Okay, let's unpack this. So for years, we've used large language models as these powerful, knowledge retrieval systems. But the big problem we all face, you face, is that they're just not reliable. They hallucinate. They confidently tell us things that just aren't true.
And that fundamental lack of reliability, it really stems from poor calibration.
The model doesn't know what it doesn't know.
Exactly. And so this research tackled that head on. The goal was to train LLMs to become genuine super forecasters, making nuanced predictions about open-ended global events.
Right, that's the mission. But LLMs need a ton of data. So what was the big problem with using, say, human prediction markets to train them?
It was really a triple threat. First, the volume was just too low. Humans were the bottleneck. You need millions of examples, not thousands.
And second, I'm guessing the data was pretty noisy. Most of those predictions are binary, right? A simple yes or no.
Exactly. If you only ask yes/no questions, your baseline for just guessing is 50%.
Which creates a really messy reward signal during training.
It does. The model can reason poorly and still get positive reinforcement half the time. It really obscures whether it's actually learning.
And the third problem was bias, I take it.
A huge distributional bias. They were so focused on US politics or crypto, it doesn't give the model a holistic worldview.
Okay, so to solve that scaling problem, the researchers built an automated recipe.
They did. They generated a data set called Open Foresight, which is about 52,000 open-ended forecasting questions, all pulled from daily news.
That's an incredible scale. We're talking something like 250,000 news articles using advanced models to just generate the questions automatically.
And these questions are specific. They're open-ended. The answer isn't a percentage. It's concrete info, like who will be confirmed as the new prime minister of Ukraine on 17 July 2025.
But hold on. How do you train a model on news events without letting it just cheat and look up the answer later? The data leakage problem sounds immense.
Oh, is a second major challenge. They were very careful. They used a static offline news corpus to make sure the date cutoffs were clean.
So the model couldn't see the future, so to speak.
Exactly. And they had this incredibly rigorous filtering pipeline.
Wait, I read that they removed something like 90% of all the candidate questions.
They did. An insane commitment to quality, because they also rewrote parts of the questions to avoid leaking the answer.
And they found that without those filters, the model actually got worse at forecasting.
It did. It just confirms that models learn to cheat very, very quickly if you let them.
Okay, so here's where it gets really interesting for me.
Right.
The actual training.
Right. They used reinforcement learning on a specialized model, OpenForecaster 8B, and it had a retrieval system, but it could only access news up to 1 month before the event.
And the reward function was the secret sauce.
It was the crucial innovation. So first, they tried rewarding pure accuracy, just for being right.
And what happened?
It destroyed the model's calibration. It would get things right, sure, but it would be wildly overconfident when it shouldn't have been.
Okay, so that didn't work. What if they went the other way? Just use the Breyer score to reward calibrated confidence.
The model became too timid. It got punished so harshly for being confident and wrong that it just started saying unknown nearly 40% of the time on hard questions.
So it threw its hands up.
It basically got scared of making tough calls. So the solution was to combine them.
A reward function with both accuracy plus the adapted Breyer score.
And that let the model be confident when it should be, but it still got a little boost for exploring difficult questions where its confidence was low.
And the results were pretty remarkable. This little 8 billion parameter model was suddenly competing with or even beating proprietary models 10 times its size.
It matched or outperformed giants like GPT OSS 120B on their test sets, yeah.
So what does this all mean for you, for the future of these tools? It's not just about a better weather report.
Not at all. The immediate benefit is a general improvement in fundamental LLM reliability.
Because the forecasting training made it better calibrated overall.
Precisely. And when an LLM is better calibrated, it is so much better at knowing what's reliable and what isn't. That is the most effective tool we have for massively reducing hallucinations.
So it's a shift from a simple fact retriever
to a reasoning engine. A true open-ended forecaster has to reason about uncertainty. It has to make these optimal Bayesian updates to its own internal world model.
And that feels like a foundational step forward.
It's a huge step, a step in a really challenging direction, but one that moves us closer to the real quest for general intelligence.
Okay, you sent over a stack of sources, and wow, if you want the one-line summary of what's changing in tech right now.
It's a big one.
It's huge.
Yeah.
Silicon Valley is basically launching an all-out war on screens. So let's drill down into this. We're using TechCrunch as our main map here.
Right. And the mission for this deep dive is really to extract the hard evidence. We're seeing this shift where audio becomes the default, turning your device from a tool you stare at into, well, a companion.
A quiet companion. I like the sound of that. But that's a massive cultural shift.
Sure.
I mean, what kind of strategic overhaul does a company like OpenAI need to pull that off? It's got to be more than just a new app.
Oh, absolutely. It is a profound top-down integration. OpenAI has unified its key engineering, product, and research teams.
All focused on audio models.
All of them.
Yeah.
And they're not just tweaking the existing software, they're building toward a dedicated audio-first personal device expected in about a year.
Okay, so here's the technical detail I think changes everything for user experience. This new standard, expected by early 2026, what can it actually do that current AI models just can't?
The breakthrough is, well, it's fluidity.
Fluidity.
Yeah. Today's models, they just stop dead the second you interrupt them.
Right. That painful, awkward pause.
Exactly. This new model will sound more natural, it'll handle interruptions, and this is the crucial part, it can speak while you are talking.
Woo! So a real conversation, not just command and response.
A true, layered, simultaneous conversation.
That immediately transforms the relationship. But if this is genuine war on screens, it can't just be one company. Where else are we seeing the groundwork being laid?
It's happening everywhere. I mean, smart speakers are already in over a third of U.S. homes, but the applications are getting so much more tailored now.
Like what? Give me an example.
Look at Meta's Ray-Ban smart glasses. They're using a 5-microphone array.
For better call quality.
For directional listening, it can isolate your voice in a super chaotic, noisy room.
Wait, directional listening. That raises the stakes on performance, but also on the whole idea of persistent audio monitoring, which feels a little unsettling.
It does. And meanwhile, you have Google experimenting with audio overviews. So instead of a block of text for a search result, it gives you a conversational summary.
And in the car.
In the car, Tesla is integrating xAI's Grok chatbot. That's Elon Musk's AI. It's designed to handle everything, navigation, climate, just through natural dialogue. Your steering wheel buttons are becoming obsolete.
And we are seeing the hardware follow that philosophy, moving into these screenless form factors, like AI rings.
Exactly. We have rings coming in 2026 from Sandbar and another one from the founder of Pebble, Eric Mizhikovsky. But it's important to remember the road here is rocky.
Right. There have been some high-profile failures.
For sure. The market is sorting itself out fast. You have the Humane AI pin, which became this, well, this widely reported cautionary tale.
A very expensive one.
Billions. And then the Friend AI pendant sparked immediate privacy concerns, this kind of palpable existential dread with its life recording model.
That brings us right to the core why. The philosophical pivot here. This whole movement seems heavily influenced by Jony Ive. His design firm was acquired by OpenAI for a staggering amount.
$6.5 billion.
And there's a certain irony there, isn't there? The chief designer of the iPhone now leading the war on screens.
And that irony is the entire point. He views this as his opportunity to, and this is the quote, right the wrongs of those past consumer gadgets he helped create.
So his number one priority is reducing device addiction.
Explicitly, the core thesis behind that massive deal is that every space, your home, your car, even your face is becoming a control surface. The AI needs to be ambient, always available but never demanding your visual attention.
So we are truly moving past simple voice command tools and into the era of constant conversational companions.
Exactly. And, this shift promises relief from screen addiction, but it leaves you with a really important question to think about. Well, if the future is a conversational AI that can speak while you talk and acts as a constant companion, how does that pervasiveness of audio tracking change what it means to be present in the world? And what new kind of passive, continuous digital dependence might this quiet little companion ultimately create? Welcome to the Deep Dive. Today we are jumping into a brand new framework for large language models. It's called Dynamic Large Concept Models, or DLCM.
Yep. And this is a big one. It's a major collaboration with folks from ByteDance Seed, University of Manchester. And it really challenges how LLMs think.
So what's the core problem they're tackling here?
Well, the thing is, traditional LLMs treat every single token, every word, uniformly.
The same amount of compute for everything.
Exactly. But, information density in real language is all over the place. Think about it. You don't give the word the the same mental energy as a critical phrase in a contract.
Right. So current models are just burning capacity on predictable text and I guess under allocating it where the real semantic heavy lifting is happening.
That's the waste DLCM is designed to fix. It
That
learns these variable length semantic concepts right from the latent space.
So it groups words together.
It does the heavy reasoning on those groups in that compressed space, and the results are pretty significant. We're talking an average performance boost of plus 2.69% under match inference FLOPs.
Okay, so same processing power, better results. It all comes down to that smarter focus.
It does. The core idea is this dynamic segmentation. DLCM breaks the input sequence into these concepts, and they aim for an average of about 4 tokens per concept.
Why 4? Is that just an arbitrary number?
Not at all. They found it was the sweet spot, really. A good balance between efficiency and making sure the model stays stable.
Okay, let's get into the pipeline. How does the model know where one concept ends and the next one, begins? It almost sounds like it needs to hit a mental spacebar at just the right time.
That's a perfect way to put it. And it happens in 4 stages. First, a really lightweight encoder gets the initial token representations.
Okay.
Then comes stage 2, the critical part. Dynamic segmentation. It looks at the local dissimilarity between adjacent tokens.
Using cosine similarity, right?
Exactly. So if the meaning suddenly shifts, the model detects that boundary and says, okay, new concept starts here.
And once you have these concepts, these chunks, the reasoning has to be really robust to handle any information loss from that compression.
Absolutely. Which brings us to stage 3, concept-level reasoning. This is where a massive, high-capacity transformer takes over, but it only operates on that compressed sequence of concepts.
So that's where the deep thinking happens.
That's where it happens. And finally, stage 4 is token-level decoding. It reconstructs the final predictions using cross-attention, looking back at those high-level concepts to guide the output.
It sounds like you have 2 completely different transformers working together, a small one for tokens and a huge one for concepts. Training that setup must be a nightmare.
Oh, it is, or it would be. They needed a pretty advanced trick to get this heterogeneous architecture to play nice.
What did they use?
It's called decoupled maximal update parameterization, or EP. Basically, they had to scale the learning rates inversely to how wide the different components were. It was essential for stable training.
And what about managing the compression itself? I mean, code compresses very differently than, say, technical English. How do you stop it from just going haywire?
That's where something called the global parser comes in. It's a regularization mechanism that balances the compression ratio across the entire batch, not just one sequence. So it allows for that content-adaptive compression while keeping it all in check.
This brings us to what you called the capacity swap. DLCM has more parameters, right? 2.3 billion versus a 1.3 billion baseline.
It does, but because that deep reasoning backbone is working on a sequence that's 4 times shorter, the effective compute, the FLOPs per step, stays about the same.
So they're just reallocating the power.
They've shifted about 1/3 of the inference compute into that smarter, higher capacity reasoning part of the model. And it pays off.
Especially on reasoning tasks.
Big time. You see gains like plus 3% on OpenBook QA. But what's really fascinating is the analysis they did, which shows this U-shaped loss profile.
So this is the trade-off. It's sacrificing a little bit of precision inside the concepts.
Precisely. The model gets much better. The loss drops significantly, right at the semantic boundaries, at the start and end of concepts. But it might have a tiny bit of degradation in the middle. It's trading token-level perfection for a much better global understanding.
And from an engineering perspective, they also found a way to speed up the decoder's cross-attention, which sounds messy.
Yeah, that irregular attention pattern could be a bottleneck. But they use a trick called concept replication, which lets them use highly optimized kernels like flash attention. It gives them a speed up of up to 1.73x, especially on really long sequences.
So if we pull all this together, the big takeaway seems to be that scaling LLMs isn't just about more parameters or more data anymore.
It's about rethinking where you actually perform the computation, shifting it towards this kind of concept-level reasoning.
It really feels like the next logical step.
A new paradigm, maybe.
Now, the sources did note that while it's great at reasoning, DLCM can struggle a bit with tasks that need super fine-grained understanding, like bool Q. It showed a small dip there.
Right, that trade-off we mentioned.
So it makes you wonder, if a future model could adaptively select its granularity, if it could operate at the token level for tiny details when needed, and then switch to the concept level for high-level reasoning, what kind of problems could that model finally solve? Something to think about until our next deep dive.
Welcome back to the Deep Dive, where we take complex research and, well, we try to give you the actionable, surprising takeaways.
Hey there.
Today, we're going to dive into a problem that just won't go away for large language models.
Yeah.
Factuality. I mean, they've made staggering progress, but we all know they still generate inaccuracies, hallucinations at pretty frustrating rates.
And that's exactly why we need benchmarks that go beyond just simple Q&A. To really get a handle on factuality, you need a holistic view that, tests memory, search, and context.
I see.
Our sources today are all centered on what looks like the new standard for this, the FCTS Leaderboard. It's a really robust suite designed to assess model reliability across 4 very distinct dimensions.
Okay, so that's our mission today.
Right.
Unpack these 4 pillars and show you where the state-of-the-art actually is. And here's the reality check right up front.
Go on.
The overall highest score achieved by any model, and this was Gemini 3 Pro, was only 68.8%.
Wow.
That means roughly 1 in 3 answers is functionally wrong. That's a massive failure rate for critical enterprise adoption, isn't it?
It absolutely is. And it just underscores why this kind of detailed evaluation is so important.
Okay, let's unpack this. It seems to start with the source of the knowledge, right? A model needs to be good at 4 different things, depending on whether it's using internal memory or provided context or external search.
Exactly. And the first pillar is FCTS parametric.
Parametric.
Yeah. This part is crucial because it tests the model's closed book internal knowledge. Basically, what does it actually remember from its training data?
And these aren't easy questions.
No, not at all. These questions were intentionally filtered. They kept only the really challenging factoids that open source models consistently got wrong.
So wait, the benchmark had to filter out the easy answers just to get a usable test? That kind of shows how far we still have to go.
It does.
We're talking about niche facts users actually care about, like trying to find the hometown of an infrequent entity, say Kevin Abstract. Honestly, I feel like I'd only score about 50% on this test myself.
Well, despite the difficulty, this is where Gemini 3 Pro really showed its strength. It hit 76.4% accuracy here, which is a noticeable lead over its competitors in just raw internal knowledge.
Okay, so that's what the models know inside their brain. But what happens when we give them the book? That leads us right to factuality with respect to context.
And the next 2 slices.
First, FFTS grounding. This one evaluates responses that are supposed to be grounded in these massive documents, up to 32,000 tokens long. And this is where we hit a really critical concept, ineligible responses.
Right, and this is so key. Grounding is necessary, but it's not sufficient. A model might be 100% grounded, meaning it didn't contradict the source document at all.
Okay.
But it can still fail because the response was just too vague. It didn't meaningfully address what the user actually asked for.
Just to be clear then, an ineligible response is technically not wrong, but it's contextually useless.
Yes.
Because it didn't provide the substance the user was looking for.
Exactly. If you ask for the key advantages of wind energy and the model just says it is renewable and clean, that's grounded, sure, but it's functionally useless.
I see.
And that dual challenge also applies to FACTTS multimodal, which requires integrating visual grounding with world knowledge.
So you need both high coverage of the essential facts and no contradiction on any facts, essential or not.
Precisely. For instance, a model describing a mural might get 100% coverage, hitting all the major points. But if it contradicts one tiny non-essential fact,
Like what?
like saying the artist's signature was small white text, when the source actually noted it was in black text below the mural, the entire answer is invalidated.
Wow. One tiny factual misstep and you score 0.
It's how strict it is.
That is strict, but I guess it's necessary for high-stakes applications.
Oh.
Okay, finally, we have FCTS Search. This is evaluating the model's external tool use with the Brave Search API. And this slice hits multi-hop queries and info on hardtail entities. So that's the niche, rarely searched for stuff that forces the model to string together multiple searches.
And if we connect this to the bigger picture, you start to see different strategies the models are using. Gemini 3 Pro got the highest search score while using the lowest average number of searches, 3.39. It's very efficient.
And others.
By contrast, a model like Grok 4 averaged 4.5 searches.
What's fascinating is the strategic difference we see with other models, though.
Absolutely. Models like Claude, for instance, they seem to choose maximum safety. They hedge.
They'd rather just say, I don't know.
Right. They'd rather say that than risk a factual contradiction. It boosts their precision score for sure, but it reduces their overall ability to answer, and so their overall score on the leaderboard suffers.
So what does this all mean then? The FACTS leaderboard clearly shows that LLM factuality isn't a single problem. It's this multifaceted challenge, right? It involves internal memory, precise context awareness, and a smart tool use strategy. And the current ceiling for the very best model is still just under 70% accuracy.
And while this benchmark covers grounding, memory, and search really rigorously, it does raise an important question for all of us.
Which is,
What challenges in factuality remain unaddressed? We still need robust, continual benchmarking for issues like handling fast-changing information or real-time video understanding. These are critical areas that aren't fully captured here yet.
an excellent provocative thought for you to chew on. And if you want to dive into those specific sub-leaderboard results and check the scores of your favorite LLM, you can find the link to the benchmark website in our show notes.